Hey guys, how you doing? It's Coach Scott with another video in Unit 3 talking about the periodic table and periodic trends. We've discussed atomic radius. Now we're going to talk about ionization energy. Okay, ionization energy. All right, there's my little arrow. So ionization energy. If we think that atoms have the same element, they're going to have equal numbers of protons and neutrons. We knew that. We learned that the first couple of weeks. So oxygen, neutral oxygen, is going to have 8 protons and 8 electrons. Neutral magnesium is going to have 12 protons and 12 electrons. All right, we say that because, well, all right, they've got 8 protons there. It's got 8 neutrons. And if you count the electrons in these energy levels, you got 1, 2, 3, 4, 5, 6, 7, 8. So it's got 8 electrons. If you add the charges, plus 8 plus minus 8 equals 0, right? So that is what we'd call a neutral atom. So, the ionization energy is the amount of energy required to remove one electron from an atom. So each electron that's removed is the energy required to remove that one electron. All right? And this creates a positively charged atom that we call a cation. So this is a calcium cation, and it shows that it's got the 1 electron removed. Now, if you notice, there's 2 electrons. Let's see them right there without the big 4 plus. There's 2 electrons in that one energy level. That's what, number 4? There's 2 electrons by themselves. All right. So the first ionization energy happens when the electron is removed from the calcium atom, all right, which is plus 20. That leaves 19 electrons, right? So that cation will have a plus 1 charge, and then that energy that's given off is the ionization energy. All right? So ionization energy is the amount of energy required to remove that electron from the atom. All right, we talked about that. So the first ionization energy is the energy required to remove that first electron. The second ionization energy is the energy required to remove the second electron from that cation. All right. The third ionization energy would be the energy required to remove the third electron. So calcium would have 20 ionization energies. Now they get such a massive energy expenditure that only a couple of them will actually make sense. All right, really 2. So let's look at lithium and beryllium, and then let's apply Coulomb's law, and that'll help us understand how ionization energy changes among the elements. So lithium, it's got 2 shielding electrons, inner electrons. It's got a Z number of 1, or excuse me, of 3. So that's 3 minus 2. It's got a Zeph of 1. So our Coulomb's law equation would be E squared over R squared, more or less, right? So beryllium, okay, it has a Zeph of 2. All right. So it's going to have a Coulomb's equation of 2k squared over r squared for the force. So which atom holds their outer electrons tighter? That's a good word to use. Think about it. And if you said beryllium, you would be 100% correct because of that Zeph of what it is. It's larger. The force is larger. So that means those valence electrons are going to be held closer to the nucleus than those in lithium. So now, since the beryllium will hold the electrons tighter, it's going to require more energy to pull an electron away. So this ionization energy of beryllium is going to be higher than lithium. Okay, so as the Coulombic force increases, the atom is going to hold on to its electrons tighter. So because they hold them tighter, these electrons are going to require more energy, and that energy is going to be the ionization energy to take them away than an atom with the lower force. So we can say as force increases, ionization energy increases. So let's think about our atomic radius. How does the atomic radius relate to Coulomb's law? Think about it. And how does it relate to ionization energy? Take a break and think about it. Since you thought about it, if you recall, as the Coulombic force increased, the atomic radius decreased. So as we went from left to right, okay, on a period, the actual radius would decrease. Okay? Now, here's the difference. As the atomic radius decreases, ionization energy would increase because it takes more energy to pull one of those electrons away. So atomic radius and ionization energy have an inverse relationship. As the force increases, ionization energy increases. It gets harder to pull one of those electrons. So let's think. Let's look at the ionization energy for magnesium, aluminum, and silicon. So let's find the Coulomb's equations for each. Then we'll order them according to its ionization energy. So think about magnesium. Magnesium in my periodic table. Okay, it's right there. It's right there. Okay. And then let's look at aluminum. All right, it's right to the right of it. And then silicon is right to the right of aluminum. So magnesium would have a Zeph of 2. So its Coulomb's equation should be F equals 2k squared over r squared. Aluminum has a Zeph of 3. So it should be 3k squared over r squared. And then silicon has a Zeph of 4. So it should be 4k squared over squared. So let's think about let's move this out of the way. Let's think about what their ionization energies will be. Let's see. So this has got more force. The silicon has more force. So it's going to have a higher higher ionization energy, followed by aluminum, followed by magnesium. So magnesium would be less than aluminum, which would be less than silicon. So how does the ionization energy change as you go across the period in the row? Well, think about it. It's going to increase. It's going to increase as you move across the period. Now, if you look at this really cool 3D chart, as you move across the period, the Zeph will increase, of course, and the force on the electrons will increase. Now that's going to make it harder for an electron to be taken away. So as I move across each of those, then of course in class, I've got that 3D printed model, and you can check it out. Ionization energy will increase across that period, or across that row. Now, let's see some of these trends. Let's look at sodium, and let's look at potassium. All right, they're both in group 1. Sodium is a little higher than potassium. So let's find the Coulomb's equations for each. They're both in that first group, so it's going to be K squared over R squared. Put that over there. All right, then the other one, potassium, is going to be K squared over R squared. But let's think. As the distance of those valence electrons grows, what happens to the bottom, the R squared? Well, it's going to increase, or it's going to get further away from the positive nucleus, which means it's going to require less energy. So potassium will have less ionization energy. It's easier to lose that electron than sodium. All right, so how does the ionization energy as you go down a period, as you go down a group? Well, ionization energy will decrease as you go down, okay, a group, because the valence electrons are further away from the positive nucleus. So as we go down the group, the Zeph stays the same, but there's an extra energy level, and that's going to move the radius further away from the nucleus because the radius is larger. That's going to make less of a force, a Coulombic force, which makes it easier to take those electrons away. So we can say ionization energy decreases as you go down a group. Okay. So let's look at our ionization energies, okay, of, all the way to xenon, which is like well out there, element 54. And let's see if we can notice some patterns. And we will definitely talk about this in class. So this is the first period, hydrogen and helium. Notice as we go from helium to lithium, number 3, what happened to the ionization energy? It dropped dramatically. Then we go lithium, then what's next? Beryllium. Then we have another drop. Then we go 3 more elements, another slight drop. Then 3 more, we have neon, then we fall down. So let's think about our different subshell types. We got S's, P's, and D's. So the first period, right? The first period, there's only 2 elements in it, or 2 electrons in it. And what's in there? Oh yeah, that's an S. And how many electrons can you have in an S orbital? 2. 1, 2. Then we go to lithium and beryllium. That's in the group 1, group 2. What do we say those were? The S block. 1, 2. I can have 2 in there. Then we go to the P's. All right, there's what? 3 p orbitals? And we're going to fill those up one at a time, right? So we got 3 p orbitals. 1, 2, 3. 1 electron in each of those 3 different p orbitals. Then, a little less energy there. We put another electron, and it starts shearing a subshell or an orbital with another electron. Then we got 5, then 6. We're full. That's a noble gas. We go right back down to potassium. Then we start going into some of the, then you got this just the same. Then we start going to some of the D blocks, and that's looking sort of weird. But then we see the same pattern again. Wow. So this just more or less proves the periodic law. So we've got the discontinuity, what I just said, between group 2 and group 13. All right. As you see those little chunks, you're going from beryllium to boron, and then from magnesium to aluminum. There's a little chunk in there. That means that the p orbital, okay, is filling up, and when we start throwing the electron into group 13, okay, it makes it easier to pull that out of the p orbital. And when we pull that out, we're actually gaining some stability. Whenever you have a full p orbital, all right, you actually have some stability. and versus with an empty p orbital. So that's good. Makes it happy. Other discontinuities. Let's think about this. Let's see if I can make this to where I can. Okay, so I can draw it. I want to be able to draw. So look at boron. It takes more energy to remove an electron from a group 2 element than a group 13 element, right? Because you're going for the S's and the P's. So let's look at group 2, boron, and group 13, beryllium, to find out why. So we have a electron in there, an electron in there. Then we've got the 2s, and I'm looking at what? Boron. And I've got 5 total, so there's 4. All right, so those are my 5 electrons in an orbital diagram for boron. Now let's do beryllium. There's 4, 1, 2, 3, 4. So I've actually got some stability, right? I've got 2 full s orbitals, but I don't have an empty orbital there. So if I can donate that electron or get rid of it, that makes the atom feel a little bit more stable. Let's see, we got that right. There we go. Hey, I did it. Yay me. So we also have the discontinuity between group 15 and 16. Let's see this. So let's think about our electron configurations, and we're looking right here and right there. All right. Why the first ionization energy for the group 16 element is less than that of the group 15 element? Now, if you think about it, it's because 15 is a half full sublevel, and it makes it more stable. Okay, I'm going to just talk more about that on my own. So let's look at nitrogen. Let's see if we can see what we're talking about. And oxygen. So I got the 1s there, 2s, 2s. All right, then I've got 3, 2p orbitals. I'm going to say 1s, 2s, 2p, 2p. We'll call that x. We'll call that y. And we'll call that z. It's just me calling them something. Okay, so let's draw our electrons. So nitrogen has 7 electrons. So let's put them in there. 1, 2, 3, 4. This is where that order of filling comes in. There's 4, 5, 6, 7. All right, so all my orbitals are full. These 3 are half full. Life is grand. Let's do oxygen. It's got 8 electrons. 1, 2, 3, 4, 5, 6, 7, and one more, 8. Now, by looking at this, it makes more sense for oxygen to be willing to, it's easier to give up that 1 electron right there because they don't like being together. They're both negatives. And that would give it half full suborbitals, which makes it more stable. So that's why, go back here, that's why there is a little drop right there, just a little drop, okay, between groups 15 and group 16. Okay, guys, this is Coach Scott. This is ionization energy. We're getting into some good chemistry right now. So we've got a couple more of these trends to study. Then we're done with the periodic table and getting ready for other bigger and better things. Okay, so this is Coach Scott saying have a good evening. Be safe, and I'll see you on the next go around.